Hello, everyone, and thank you for taking the time to join us today for this exciting webinar being brought to you by Cintiqa Instrumentation. My name is Tanya Coulthard, and I will be your host and one of your presenters for today's webinar. Our webinar today is entitled Introducing the NGB-R, a disruptive 4D bioprinting system, and we'll work through the NGB-R workflow, hardware, and software demonstration from the user's perspective. This is the third and final webinar in our mini-series introducing the NGB-R system and Cintiqa's newly formed partnership with Poitis to distribute the system within North America. Today we'll have three presenters, myself, as well as Antoine Jacot and Michael Garcia, both from Poitis. We will each do a quick introduction of ourselves before our section within the webinar. During the webinar, I will give a brief overview of the NGB-R system as a recap for those who were unable to join the previous webinars. Michael and Antoine will then take over, reminding us of some of the finer details about the laser-assisted bioprinting, and then we'll move into a system demonstration. As we may have some time at the end, they will then recap some of the very interesting applications that we talked about a couple weeks ago in the last webinar. However, before we begin, I'd briefly like to mention a few housekeeping items. We do anticipate that today's presentation will be about 45 to 50 minutes. This should leave us with some time at the end to answer any questions that you may have. Please use the Q&A dialog box to submit any of the questions that you have throughout the presentation, and I'll work with the team towards the end to get through as many questions as we can. We will create a transcript of the questions we do answer and those that we may not have a chance to address during the 60 minutes that we do have together. We'll distribute this document in the next couple of days. Please also note that we are recording today's session, so if for some reason you lose the connection or you can't hear everything clearly, you will have access to the video file later. So as we get things started, I mentioned I'll do a brief introduction of myself. I will be one of your presenters today, and I manage the imaging and molecular divisions here at Cintiqa Instrumentation. As discussed in more detail in the first webinar in this three-part series, Cintiqa and Poitis formed a partnership back in January, and this allows Cintiqa to distribute the NGB-R system within North America. Cintiqa's headquarters are in London, Ontario, Canada, and we also have offices in Texas as well as in the Netherlands. Poitis, the manufacturer of the NGB-R system, is based in Bordeaux, France. So as I mentioned earlier, today I'll give a brief overview of the NGB-R system to help those of you who didn't attend the previous webinars to get a little bit caught up on the features and the hardware. And then we'll move on to a brief review of the laser-assisted bioprinting, which Antoine will give. And then both Antoine and Michael will talk about the workflow of the NGB-R system, starting first with the CAD software, and then we'll move into a hardware review and show you some videos of the system in action, and we'll finish up with a look at the ViewPrint software. Towards the end, as time allows, the guys will review some of the applications that we talked about in the previous webinar. And then finally, I will rejoin the conversation to host the Q&A at the end. So again, if you have questions as we move through the webinar today, please feel free to use that Q&A dialog box to enter them, and I'll work through with the team at the end. As we get things started, I would like to launch our first audience poll. And this is really just to start to get a little bit more information about people, learn a little bit about those who may have attended the previous webinars in the past. So the first question has to do with, were you able to attend or participate in either of the first two webinars within this session, either in person or on demand? And then secondly, this will look familiar to those who've attended before, but we have some new people attending the webinars this time, and we wanted to get some more information on what type of work they're doing or research that they're involved in, just so we have a sense of the people participating today. Okay, I'll give everyone just a couple more seconds to respond to those. Wonderful. Thanks for taking the time to answer those. We do appreciate it. And now, as we get things started, I will again start with a brief overview of the system. The first thing for those who didn't attend the first two webinars, most people have the question of where does the name NGB-R come from? And so it comes from the name Next Generation Bioprinting, and specifically the system has been designed for research applications. So that really helps me to get the acronym correct as we're talking about it going through the presentation. As Antoine and Mikhail will walk through a little bit later, the NGB-R platform is composed of two different parts. The first is the CAD, or the computer-assisted design software, which allows the users to design the cell patterns that are required to create the tissue architecture in a layer-by-layer manner, while also considering printing of other structures such as the extracellular matrix and different compounds that may be required to finish up the fabrication of the tissue that you're trying to print. Once the fabrication steps have been planned and designed and saved, everything is transferred over to the HMI, which is the human machine interface software on the NGB-R computer. So this computer is actually on board the physical hardware of the system. And from there, the user would program the bioprinting job, add the sequences in, and perhaps add in any steps to do with using the microscope or the UV light source, which we'll talk about as we go through the hardware. And once everything's programmed, the system is able to take control and proceed through the automated steps, which have been programmed to complete that fabrication process. We'll see the system in action in a few slides, but this is really what the hardware looks like. So the NGB-R system is actually a biosafety cabinet, so a BSL2, which can be used to prepare the cells and the bioinks and everything that you need to get ready to print. There is a 6-axis robotic arm on the system, which we'll see again in some videos in future slides. This is an industrial grade arm, which helps provide the precision that's necessary to perform the intricate cell patterns and printing processes that would have been programmed within the CAD software. There is that touchscreen interface, which is where the HMI software is located, and this allows the users to really sequence their print job that they wish to complete. There are different techniques used within the NGB-R system. So there's the laser-assisted bioprinting head, which we'll review in a couple of slides with Antoine. There are also optional additional heads. So those will be bio-extrusion, microvalve, or inkjet heads, which can be added onto the system and would be configured just to meet the needs that you have for your specific applications. There is an integrated microscope, and this allows us to ensure the precision of the instrument. So you may be able to take a microscopic image of your tissue that's being printed after each step or at prescribed steps as you go through the bioprinting process. Not shown here, but what you will see in some of the future slides is the multi-wavelength UV light, which can help with cross-linking and other steps that benefit from having the capability directly in the fabrication process. And so finally, the system, as I mentioned, does have 3 bioprinting options. The one unique to the NGB-R is the laser-assisted bioprinting, and Antoine will go through a bit more detail and remind us of some of the features and benefits and why we would use that. The system can also be configured to have optional bio-extrusion or inkjet or microvalve heads included, and those would be used to complement the printing of the cells and laying down different extracellular matrix or scaffold compounds as well. And so by including these 3 different printing techniques, the current bioprinting protocols that perhaps some of you have spent a long time developing can easily be transitioned onto the NGB-R system. However, in using the laser-assisted bioprinting techniques, the cell patterns and the cells will really experience a lot less stress, as Antoine will go through, and therefore increased cell viability as to not be exposed to the shear stress that would be placed on the cells during extrusion or inkjet techniques. So again, Antoine's going to take over at this point and review some of those specifics in terms of laser-assisted bioprinting and the benefits of it. So Antoine, at this point, I'll turn things back over to you.
Hello, Tanya. Thank you very much. Both Miguel and myself are very happy to meet with all of you again today. So yeah, for those of you joining us for the first time, my name is Antoine Jaco. I'm a sales manager at Poetis, and I'm joined together by my colleague Michael Garcia, working as a business application manager in the NGB-R team. So Syntec is Poetis' partner across North America, as Tonya mentioned, as we want to facilitate the access to that technology for American and Canadian users. So this one today is a very exciting session. In the past ones, we've covered some of the key features and specifications of the platform, as well as a few possible applications of 4D bioprinting. But today we're going to show you exactly how the instrument operates from the initial layer by layer tissue architecture design all the way through actual automated biofabrication process. Yeah, so before we step into the demo, please allow me to give a quick recap of the laser-assisted bioprinting technology for those of you who did not attend the previous couple of sessions, since, as Tonya mentioned, laser bioprinting really lies in the very core of the platform. So laser bioprinting is a unique nozzle-free technology that has the capacity to give the user full control over spatial distribution of cells in the bioprinted construct, thanks to customizable micro patterns in which cells are printed with, literally in nanoseconds. So this droplet pattern approach has a genuine and direct impact over self-organization of cells, and hence biological functions emergence and proper tissue morphogenesis post-printing. So basically, it allows you to work with very high cell concentrations of up to 100 million cells per ml, with the capacity to transfer up to 10,000 droplets in a single second. I'm going to stop here, but if you want to find out more about how it works in more details, I would recommend you to watch the on-demand recordings of our previous webinars on Cintiqa's website. They're totally free of charge, and Tonya can copy the links in the chat box here if you're interested. So unlike with conventional extrusion-based bioprinting, here living cells can actually be directly printed alone, just in their culture media and with the laser bioprinting technology, while the extracellular matrix layers may be added with complementary nozzle-based bioprinting heads. So that cytocentric approach really changes the actual way that we regard and choose biomaterials. What I mean here is that we're not trying to limit shear stress to a maximum, since there simply is none, right? It's a nozzle-free technology, no shear stress here. So no need to worry about injury limiting biomaterial properties. Instead, we're just going to select a biomaterial over another based on its biological properties and its capacity to help biological functions emerge. So you've probably understood already that one advantage of transferring cells with laser bioprinting lies in the great cell viability ratio that we get. That's about 93 to 95%, as the technology really preserves cell integrity throughout the process. Yet another benefit is the control that we have over resolution by easily adjusting either the cell concentration in the media or the media volume on the laser printing head, or simply the laser beam energy level. By adjusting those parameters, you can control the size of the droplets that you transfer, and therefore the actual number of cells in each and one single of them. So you could get pretty close to single cell bioprinting with 1 to 3 cells per droplet, or typically work with those cellular spots of 50 to 100 cells per droplet that we usually work with, or even transfer cell aggregates and spheroids, depending on your applications. But the biggest advantage lies in the possibility to work with cellular patterns. So to gain total control over the precise distribution and organization of cells within the bioprinted tissue or construct. And as you can see here, this is a key component of 4D bioprinting because it focuses on tissue morphogenesis control over time, as we developed in the previous session a couple of weeks ago. So this recap being over, now let's give you a taste of what working with NGB-R is like, starting with the overall tissue biofabrication workflow. So there are basically 6 main steps towards a bioprinted construct. Everything starts with designing the actual architecture to be printed. That makes a lot of sense. But so NGB-R comes with a computer-assisted design software that can be operated from any computer in which you will use to either create tissues from scratch or load 3D.stl files and convert them into bioprintable layers. So in about a minute, Mikhail will give you a demo. So make sure to stay with us. The second step is to transfer that CAD file over to the NGB-R instrument, either with a USB drive or just through the network. And once the file is loaded to the platform, then you have the possibility to sequence your printing jobs, send the order, which jobs must be executed, or adding new ones like capturing an image with the onboard microscope, and so forth. So you could choose to have, say, a fully automated non-stop process, or to have the instrument stop at every single step so that you can check it out. It's totally up to personal preferences. The last step before bioprinting is to simply load the bioinks. So we'll show you in videos exactly how this is done in a few minutes. And then to initiate biofabrication, all you have to do is select Start Bioprinting in the NGB-R interface, and the instrument will crack on printing the sequence that you have loaded. Finally, you may visualize the bioprinted construct either through the cabinet window or with the onboard microscope if you have opted to have one. So now I'm going to pass it over to my colleague Mikhail, who will take you through the actual tissue architecture software and show you how easy it is to create tissue layers with NGB-R.
Hello, so I'm Michael, and today I wanted to introduce you our computer-aided design software called TAD for tissue architecture design. So the objective for us was to propose a user-friendly software adapted to the use of scientists. And here I will show you how you can process for the design of your experiment. So here, the first step, you have to choose which kind of plate you will use for your experiment. So it can be 6-well plate, it can be 12-well plate, or it can also be 1-well plate. So here we'll pick up this one, the first one. Okay, and now you can visualize 1 well. First step is to choose which kind of ink you will need for your experiment. So I will take as an example the creation of skin model. So for skin, we have different kind of cells. We've got fibroblasts and keratinocytes, and we will also use materials. So cells are printed with the laser, and the material is printed with the microvalve. So first kind of cell that we will use is fibroblast. Okay, now you can here give the size of your droplets. So when you print with laser, of course you print droplets. So if you have an idea of the size of these droplets, you can enter it here. Usually we usually do some experiment before to know that. So here we know that it's 200 microns in our conditions. And you save changes. Here you created your first ink. Then with microvalve, you will print collagen. Okay, the radius is 300. And here it's more accurate for the visualization of what you will print. You save, and now I will add a second ink with the laser. Here you can pick up a new color. Okay. Okay. And here you created a new ink that you will print with the laser. So it's keratinocyte. And the radius is 300. Okay, save changes. So now you created all of your inks that you will need. And so bioprinting is a layer by layer process. So now layer by layer, you will define what is your pattern and what you want to print. So first step, I want to print the hydrogel with a microvalve. So here you see it's really user-friendly. Okay, you can center the pattern. Then you can move it, you can resize and fit it to the layout. And then, so you can play with the spacing between the patterns. So you've got different kinds of patterns. It can be a grid, it can be equidistant, it can be free draw, gradients. I will show it later. And now you can adjust the spacing between your droplets. And if you know the real size, you can obtain a confluent layer of it. Doing this kind of process and this kind. So either you can do it manually like that, or you can enter here the real spacing between all of these patterns. Okay, and now that you've got your layer of collagen, yeah, just I want to precise something. If you want to play on the thickness of the collagen, for example, or material that you will print, you can here play on the spacing between these patterns, or you can play on the pressure during your experiments. So then you can repeat the layers. Okay, I've got some issues. I will go back. Okay, so sorry for that. So here I can center it. I adjust it. And then, of course, you can repeat the layers. Now I will add the layer of fibroblast. So here, fibroblast. Okay. Again, what you print is droplets with the laser. You can center the pattern. So here you can choose which kind of pattern you want. So meaning it can be a grid, it can be equidistant, it can be a free draw. So you can add some droplets by hand. It can also be a gradient. Then you can play on different parameters with this gradient according to the spacings. The spacing that you want between the droplets, you can design easily a square, an ellipse. Let's pick up equidistant. That's what we usually use. Okay, we fit it to the layer, and now you've got your layer of fibroblast. And of course, you can repeat it several times, and then you can adjust what you want, meaning that to obtain a dermis model, you print first a layer of collagen, then a layer of fibroblast, and you repeat this again and again. Then the last layer, usually for the last layer, what we print, so here I have to create again a new ink, select color, sorry for that. Okay, okay, and this is keratinocyte. Here. Okay, so here for this last layer, so we print keratinocyte. We can place it here in the middle. We fit to the layout. So if you want to resize, you can resize it by hand to choose the good region that you want. And then here's the spacing. So we can choose 1000. So you can do again it manually or precisely here. Okay, so and the last layer is fibroblasts. So what you can do also, if you want to use different cell type, is to print a new pattern. So it was a recent publication of L'Oréal where they want to use different kind of keratinocyte, and you see it's really easy to do that. You can add another population here with a new pattern. So it's really easy to do that here. So let's say this is a new kind of, sorry, of keratinocytes. And then you can resize and place your cells easily here, and it fits with your well. And so it's really easy. You can add as much as you want as cell types. So you can do that by quarter. And then another features, which is interesting. So let's go back. It's the mask. So you can add a mask. This one. So again, you can displace it here. You put it in the center. Something that you can resize. And here again, if you want to print different cell type, you can do that like this. So it's really easy, it's really fast. And then, of course, you can resize and you can repeat it many times. You can add as much cell type as you want. And again, if you want to add another mask, you can do that. Here, there is different kind of masks. So this is a square one, but you can also use a circle. So it really depends on the kind of application that you want. And you can, of course, resize this mask. Okay, then another feature that I wanted to present is the one with extrusion. Okay, let's add this one. So again, extrusion. So here we don't print droplets. It's continuous lines. Again, you can choose from experimental data the size of your lines. Let's say that it's 100 micron here. Okay, save changes. No. Okay, 100. Okay. Now, one application that we developed is to create grids, something that we had during our experiment for a customer. So it's pretty easy to do that. You just have to choose the size of your grids. So you can enter it here or do it by hand as I do. Then repeat the pattern. Oh, sorry. Up here, repeat it. Okay, and then doing this. Here you can obtain easily a grid. And one application that you can do is to create this grid with a material and then with ViewPrint go and print cells inside. So this is during an experiment if you want to visualize and do it, or directly do it from this CAD and say, okay, I will create this grid, and then with the laser I will print, I will print cells inside these grids. So for this, I have to create patterns with the cells. I can resize it and do it like that. So it's really easy, or you can do like that, or of course you can do it again manually using this one with the free draw and say, okay, I want to print cells inside these micro wells, and you can design as you want. So I think that's all for me. Antoine?
Yeah, thanks a lot, Mika. I will take over from there. And so hopefully you should be able to see my screen again. Yeah, so I hope that you guys found this demo insightful. Thank you very much, Mikael. Now it's time to show you the NGB-R operating. So we've got a series of videos coming up for each and every module that we have, starting with the cabinet itself. So before being a 4D bioprinting platform, NGB-R is actually a type 2 biosafety cabinet. So although it's quite space consuming, the instrument can fulfill several purposes and therefore supplant an old cabinet you wanted to see replaced, for example. So you may perfectly use it for all your cell culture and related work, as well as for all your bioprinting work, obviously. Now, operating the instrument is done through a large touchscreen interface with Poetis's human-machine interface software pre-installed. So the editor area that you see here allows you to load your tissue designs and to create /edit/organize sequences. So for each construct that you have, you may either select the type of receiver that you want to work with, as well as the specific wells that you wish to print into. You can create and sequence your printing jobs at just all imaginable parameters of every single printing head. You can review the whole sequence and so forth. So the printing area that you will see in literally a few seconds, on the other hand, right there is the launch pad for bioprinting. So from there, all you have to do really is click start to see the design being bioprinted. But you can also use the HMI software to clean up printing heads, turn on optional imaging devices, run calibration, and so on. Now, here is how to load either ready-to-use bioinks or specific biomaterials directly to the nozzle-based bioprinting heads. So to both the bioextrusion and drop dispensing devices that we also call inkjet or a microvalve. So the NGB-R is compatible with 3 and 5 ml cartridges, which can easily get connected, as you just saw, to the instrument and inserted into the print heads. Simple as that. Now, once the print head loaded, you're ready to bioprint. And I'm only talking of the nozzle-based printing it here. So here's how it's done. The extrusion and inkjet heads can come either standard or thermoregulated if needed. So that thermoregulation goes from 4 to 60 Celsius degrees if needed. That's an option. And the extrusion head prints filaments of up to 100 microns, while the inkjet head does drops of up to 100 NL. Now, an optional single or dual wavelength UV lamp can be added to the instrument as well. And also added to the workflow itself for cross-linking and polymerization purposes. So it's either 365 and or 405 nanometers. And typically, so this is a printing job that may be very easily included into the bioprinting sequence through the human-machine interface software beforehand. Now let's move on to the laser bioprinting head and show you how to load the bioink here. This is probably the question we get the most. So I'm very happy to be able to share this video with you guys. So as explained earlier in other sessions, cells here are printed directly in their culture media. So here's how it works. Just simply deposit a drop of that cell media onto the ribbon. So the gold metallized substrate that we talked about during the last session, and gently spread it across. Then you just simply place the holder on top of the laser bioprinting head and you're ready to go. So it's, yeah, 15 to 20 second job, basically, to just load the cell media to the laser bioprinting head. Once that's loaded, then you may initiate the printing sequence. So here again, the robotic arm is automatically going to flip the receiver upside down when approaching the laser head as we print against gravity here. So as you see now, transferring cells is an extremely fast process that literally takes a few nanoseconds to complete. And here the robotic arm stops working because if you had a whole sequence loaded, and again, well, here that's just a 1 second thing, but if it's part of a whole, multi-layer tissue bioprinting, then of course the sequence would not stop there and it would basically carry on with other jobs. Now, as discussed during the last session, the NGB-R platform can be equipped with an optional microscope for either quality control and or target bioprinting purposes. So Quality control means that you'll be able to visualize every single layer of your constructs if you wish, without having to take the sample out of instruments. So that's a lot of time that you can save and a lot of data that you can collect that can prove very helpful. Target bioprinting, on the other hand, also called viewprint here at Poetis, is an amazing feature that would let you view the receiver and select the exact spots where cell droplets must be distributed. And that's exactly what we're going to see right now. So here's viewprint in action. The first step consists of you selecting the type of receiver that you want to work with and the specific well that you would like to image and work on, as you can see on the screen right now. Then you just simply add the imaging job to capture an image. So typically it would be the microscope if you have opted for this option. And from there, at the touch of your fingertip, all you have to do really is just to select the spots to distribute cells into and the bioprinting modality to use. So laser bioprinting, of course, being the most precise one, and therefore the one that we recommend using. But I mean, if you want to do it with the drop dispensing device, that's fine. So as you do this, afterwards, as soon as you click start, the robotic arm will position the substrate right at the right spot, and cells will get transferred to the spots that you've indicated the system. And that's exactly what you're going to see now. So cells being printed in a few microgrids that we've selected beforehand. So as a recap, there are three main steps to viewprint. Step number one is to visualize the receiver through the microscope. Done. Then just select the spots where to just distribute cell droplets into, sorry. And then target bioprinting and part printing, controlling through yet another image capture with the microscope. All right, so you would take basically a picture before, a picture after as a quality control step. And in these examples, we target bioprinting mesenchymal cells into microgrids that were coated with collagen before, just to ensure smooth landing and promote proper cell adherence. So as a recap, there are four main applications for the viewprint feature. The first is to distribute cell droplets of one or an additional cell type. So, you know, it could be working with several cell types at specific spots on the tissue. The second would be to incorporate cells into very confined microwells or microgrids. Another example here would be to print cells directly onto a chip, like you know, custom-made organ on a chip devices that more and more people are actually relying on. And one last example would be to create, for example, networks of cells or multicellular models with MEA chips, so standing for microelectrode arrays. So as an example, we discussed with people at the moment that are very interested in distributing neural cells on such a chip, just to create a network that can be activated with electrodes. So to conclude, the bioprinter here is really a multi-model platform with 3 embedded bioprinting technologies that can meet most application requirements and serve many purposes, really, including well, 3D tissue models, of course, organ models and organoids, cancer and tumor models, as well as high throughput screening, and very custom applications which require precise distribution of cells, as we've just seen with viewprint. So all these are actually part of what we call advanced tissue engineering, and they serve a great deal of applications, such as well, basic and fundamental biology, oncology and immuno-oncology, drug screening, pharmacology, translational and medical research, but also bioengineering for clinical research. Well, thank you very much for attending. This is the end of my presentation. I'm going to pass it back on to Tonya, who's got some audience poll, and then we're really happy to answer any question that you may have.
Great. Thank you so much, Antoine, for that, and Mikhail for your software demonstration as well. I did want to just run a quick last audience poll, just wondering if following the webinar you wanted me to reach out to talk more about maybe some short-term needs about the system, send you the link for the webinar, or if you were really just here to learn more about some interesting technology. So please feel free to take a second to answer those. While we're doing that, if there's any questions that have come up during the webinar, please feel free again to use that Q&A dialog box. I'm more than happy to work through the questions we have, but if there's extra, I'm happy to see those come through as well. So at this point, I'm going to end the poll and we'll start the Q&A session. So an interesting question came through as you showed that UV lamp in that one of the first slides of the software being used or the hardware being used. If the UV lamp is used for cross-linking different printed compounds, if there's residual compound in either the extrusion or the inkjet heads, would it not then be also affected by the UV light being placed onto the sample, just due to the close proximity?
Yeah, that's a good question. Maybe from the video, it seems that the UV lamp is located right next to the printing head, but it's actually way behind and quite under. So basically, there's no direct light, there's no direct UV light that may reach whatsoever the printing head. So there's absolutely no problem with this.
Perfect. We didn't go through the exact process of laser bioprinting in this webinar, but there is an interesting question about how does the laser assisted bioprinting work? And perhaps I'll take a stab at answering this one, and then Antoine or Mikhail, if you want to add to it, feel free. So we didn't show the slide, but I do invite you to look at the first or second webinars. My colleague has placed the link in the chat box for all of the attendees. But basically, you saw the metallized substrate that the media with the cells was spread across. That sits on top of the laser head, and the laser is shone up from underneath as it hits the metallized substrate. So it's a glass substrate. Energy is released, and that basically allows a droplet to be released from that media layer, shooting upwards towards the plate that you're printing onto. And as we saw in the video, that plate is flipped upside down quickly for that to occur. So the inkjet, or sorry, the media jet goes upwards and basically prints the pattern onto the media or the plate that you're printing onto. Further to that, Antoine, perhaps if you want to address this, can laser-assisted bioprinting be used to make a thick tissue? And I would say with that, you're using multiple layers and multiple substrates to kind of build up that and implant cells at different points. But if you wanted to expand on that.
Yeah, I mean, good question. Of course, I'm gonna answer, but Daniel, please feel free to watch the couple of on-demand recording that we have of the past couple of sessions, because we really delved into the laser-assisted technology, and everything was quite well detailed. So yes, you can rely on this technology to make thick tissues. Basically, the thickness of the tissue really depends on the actual tissue architecture that you've designed. I'm sure you've comprehended with Mikhail's demonstration that you can build as many layers as you want. So, well, there's no limit, no technology-related limit to the number of layers that you can produce, hence to the actual tissue thickness. Now, cells are usually printed in between layers of extracellular matrix, usually being biomaterials that are selected. So in this instance, I think Mikhail chose collagen. But yeah, it's totally possible to make a thick tissue with this technology.
And yes, I just wanted to add something. So here we have been printing different kind of tissues, and for example, regarding skin, we have been printing models of few millimeters in terms of thickness. And just regarding the laser, I just wanted to add that an important thing with the laser is that according to the energy that we choose, and the concentration of the cells in the ink, we can play on the size of the droplets that we print, and also with the quantity of cells that are present in these droplets. And again, we can also print materials with the laser. And so here we have been controlling the thickness of the layers of collagen using either the laser or either the microvalve.
Perfect. Sticking on the topic of the laser, another question, is there any effect such as heat on the cells caused by the laser hitting the metallized substrate on the slide, which the cells are placed onto? So I'll take a stab at answering that, but again, if you guys want to add more. The team at Poitis, as they've discussed with me, spent a lot of time picking what metal would be used for that metallized substrate to ensure that there wasn't heat generated when the laser was to hit it. So that's where gold is used. And it sputtered basically onto that cover slip, the glass cover slip. As the laser hits the gold, there's enough energy released to release that inkjet, or the ink, or the droplet, but it doesn't create heat. Therefore, there's no damage to the cells or risk of heating the cells or material in that process. Perfect. Moving now to a little bit more about Mikhail's side of the demonstration. So Mikhail, you showed the different options to choose a single well, 6 well, different sized plates. Are the wells within the software predefined, the sizes of them, or is it something that can be customized beyond what would be, say, a normal or standard sized plate?
So that's a really good question, and it's something we have been discussing a few weeks ago with our engineers. So now you can pick up some predetermined plates, but of course we could add more plates. So it's something that we can totally do. So we just have to enter. We go on the website of your supplier. We just pick up the size of the wells and we enter it really easily inside our database. And so of course you can do that.
Perfect. Another question along those lines is, does the software the TAD software where you're doing that design, does it need to be connected to the printer? And is that software, I guess, free to install on the computers that the users have? And so I'll take the stab at the first part in terms of the TAD software is on a separate computer. So Mikhail was doing that on his normal computer within his office. And then all of that information that is saved is then transferred onto that HMI software, which is that computer attached to the NGB-R. And then those cell patterns and different patterns are used to basically sequence the fabrication steps that are needed. So put in order, replicated layer by layer to create the tissue that you're looking for. What I don't know the answer to, and perhaps Antoine, you can help me with, is that software free to install on computers of their choice? Is there any limitations there?
Yeah, I like that question. So it's a license-free software. That's a great news. And what it means is, well, basically, if you've purchased NGB-R, then you can install that software on as many computers as you want. Usually, and there's a good reason for that, NGB-R being quite an expensive instrument and a multimodal platform. There's usually not a single person using it. It's usually an entire team or entire teams actually with different applications using the platform. So each one of them needs to have at least, you know, the CAD software available on their computer so that they can design their tissue constructs. So yes, it's a license-free software that can be installed, and then as you, Tonya, explained, then it's quite easy to transfer over the file directly to the platform.
Perfect, thank you. Another question, are there any limits to the types of cells which can be used with the NGB-R? And where would someone typically source those cells? And so I'll take a stab at this, and again, the guys can add to it if they'd like. based on previous webinars that we've had and conversations that I've had with the team, there really are no limits to the types of cells that would be used. The team has used keratinocytes, fibroblasts, all types of cells, including different types of stem cells. So pluripotent stem cells, embryonic stem cells, human cell line, human cells, so taking them out of a patient, or even cell lines, which are typically used as well. I guess to add to that, a question that we also often get is, can the system be used to print spheroids and or organoids and not just cells? And so, Antoine, perhaps you want to answer that part of the question, because I know we often get that.
Well, you said everything. We've really tested this technology with plenty of different cell types. I think it was 26 in total, and even plant cells, and every time it was pretty successful. The cell variability ratio changes a bit depending on what cell type you work with. So obviously, fibroblasts, always a little easier to deal with than say neural cells. But even for those more, trickier, more complicated cell types to work with, it's usually in between 93 and 95% in terms of viability. And that's the main reason why laser bioprinting is such an interesting technology. Is of course you can do a lot of patterning, but you can also preserve cell integrity throughout the process. And to me, it's a very important factor.
Perfect. Perhaps for Michael, do you have a database of printing templates that people can choose from for different types of applications?
That's a really good question, and it's also something that we've got in mind to create a library. So actually what we propose is to help the customers regarding the parameters that they will require for each kind of cells, each kind of material. We can provide some data sheets about that. But yes, it's something that we want to do, a real library inside provided with the machine. But actually what we provide is this kind of services to help regarding the kind of cells you use and regarding the materials.
Perfect. Another question is how do you go about printing complicated 3D parts? And I'm going to perhaps take that a step further in terms of complicated 3D tissues. And can these be imported and have the software basically take over and do everything automatically? And I think this question was asked perhaps earlier on in the webinar, and I hope that what we were able to show was that you design it layer by layer, but once you've used the HMI software to program that sequence of fabrication steps, that really the computer does take over and everything is built automatically once you've told it the different shapes and the structures and the thicknesses and the sizes that you want and at what point you want cells included in that material or that scaffold as well. Antoine and Michael, I'm not sure if you wanted to add anything more to that.
Yeah, so basically there are two ways to use the CAD software. There is the way Michael demonstrated, in which you're going to create a tissue from scratch, and then save that file as a .bio. That's the typical POTIS saving format that we use. Another way to use the software is to import a .stl file, so a 3D image of an object. And then there's an integrated slicer inside of the software that will basically automatically slice that image into layers. That is then automatically saved again as a .bio so that the bioprinter understands it. It's just a language thing, right? So basically, yes, the software can turn a 3D object into 2D layers that can later on be bioprinted by NGB-R.
Perfect. Excellent. A couple to do with the hood and it being closed. And so I'll take a stab at the first one. Does the hood have to be closed when doing printing? And what you didn't see, or perhaps you did, is that there is actually a film on that hood, which prevents any stray laser light from coming out. And so it would need to be closed for any of the laser assisted bioprinting steps. Antoine or Mikhail, what I'm not sure of is if you can operate the system with it open and only use the extrusion or the inkjet heads.
So yeah, for security reason, of course, yes, it has to be closed because there is inside. So there is, as you said, there is the laser. So for security reason, we've got a specific treatment of the glass, and the glass has to be closed to use the laser. But also we've got a robotic arm moving inside. So of course, if the glass is not closed, the robotic arm cannot work. The laser either. So the only use that we got with the hood open is like a usual cabinet to go with the cells, with the preparation of the materials and everything else.
Got it. And just a follow-on question to that, how do you, and perhaps you can describe a little bit more how the hood works, just to ensure that as that glass is opening, that the laminar flow is maintained and that the sterility within the hood is maintained as well. I presume it functions very much like a normal safety cabinet in that if you raise that window below a certain speed, you're not ripping it open very quickly, that the laminar flow would be maintained.
Yeah, exactly. I don't remember if I mentioned it during this presentation, but we definitely did in the previous one. So it's a type 2 biosafety cabinet. It's very, very similar to other standard biosafety cabinets. So it definitely works and operates the same way. Now there are two types of bioprinters that POETIS is currently engaged with. There is NGB-R for research, and here everything is very much similar to another research biosafety cabinet. And there's NGB-C, which will target the clinical market, so for definitely clinical applications in which sterility is one of the most important factors. And so the cabinet for that second bioprinting platform will be different. It will be an entirely closed environment to preserve sterility to 100%. So I'm not sure whether that person was referring to NGB-R or NGB-C. Mikhail, is there anything you want to add to that?
Yes, I just wanted to add that, yes, I said that it was a usual cabinet, but contrary to usual cabinet, when you close the window, of course, the flow stops. In our case, it's adapted. So meaning that the flow doesn't stop. It's adapted to the fact that the glass is down. So sterility is maintained.
Got it. Perfect. We've got just a couple minutes left. If there's any remaining questions that people in attendance still have, feel free to enter them in the Q&A dialog box. There is one left, and it relates back to when you were talking about viewprint, and you were showing how different wells could be selected and then have the cells printed within. Is there any way to automate that process and have it be more software-based and removing the inaccuracy of the human side of things? And if I can add to that, perhaps we can talk about it with respect to wells that you are planning to be printed, as well as then wells that are on, for example, the electrode array plate that you were talking about towards the end, Antoine.
Yeah, I'm just trying to figure this question out. So is there a way to automatically make this selection? So I guess that person is referring to the different wells that we selected to distribute cell droplets.
Yes.
There are two ways to do this. So from Mikhail's demonstration, you've seen that you can actually automatize that with the CAD software. So for example, you could have a grid bioprinted with extrusion, and then have a pattern of cell droplets inside every single well. That's a way to do so. And if you want to distribute cell droplets onto an existing object, then of course you would need to rely on viewprint, the function that we've demonstrated. And here there's no way to automatize this because, well, you need to select the wells that you wish, or I mean the spots where you want cells to be distributed. So the computer or the instrument does not know in advance, you know, the exact spots that are of interest for you. So no, there's no other way to do it, but the main way we showed. Now, maybe that person is worried about precision. So this is what I would like to add. Before you distribute cell droplets, you can really zoom in the picture to a maximum. We didn't show it, but with the microscope, that's the beauty of having a microscope. You can really zoom into a few microns, and so the area, the spot that you will select will be with very high precision.
Perfect. Thanks, Antoine. I think that's all the questions that were asked, and that's perfect timing because we have reached the 60-minute mark. And just to be respectful of everyone's time, I do want to end the webinar now, but we will be sure to answer any questions that you may enter as we're finishing up, or feel free to email us at Syntica. The email address is there on your screen. I do want to thank Antoine and Mika for joining me today as presenters, as well as for taking the time to address so many of the great questions that we had, and for your participation in the Q&A as well. It makes it a lot more interesting and fun for us when the questions come through, and they're really quite interesting. I do trust that we've been able to provide you with some exciting information about the possibilities of 4D bioprinting and the laser-assisted techniques with the NGB-R. If in the days and weeks to come, you're thinking about the system, the information that we presented, and you have more questions, please do feel free to reach out to us here at Syntica, and we'd be happy to address them. If I'm unable to answer those questions, I'll of course reach out to Antoine and Mikhail to help get those answers for us. So thank you all again for taking the time to participate in the webinar today, and we do look forward to seeing you at a future Syntica instrumentation event. Thanks so much.